for evaluating functions, if I have a function written in function notation, and then I say, what is f of 4? We would take the 4 and substitute it in to where we see an x. And you're always going to be safest if you use parentheses to substitute in, right? So this now becomes -2 times 4 squared, right? It's the 4 being squared that has to happen first. So that's 16, right? And then plus 1. So f of 4, right, equals -32 plus 1. F of 4 equals -31, right? So again, in this step, make sure when you substitute in, you use parentheses around what you're substituting. You'll make less mistakes. Okay, for solving equations, when we have equations with a lot of fractions, there's different techniques we can use. I believe the book calls it, fraction busters or whatever. But basically, if we multiply both sides of the equation by the least common multiple, so in this case, I have denominators of 2 and 3. So the least common multiple of 2 and 3 is 6. So if I take the whole left side of the equation and multiply it by 6, and the whole right side and multiply it by 6, I can eliminate my fractions. So -1/2 times 6 is -3x, because we're distributing, right? So then 6 times 1/3, right, is 2. And then the 6 times the -2/3, right, is -12/3 or -4, right? -12/3 is -4. And then the 6 times the last one, the 2, is plus 12, right? Equals 0 times 6 is 0. So now we have like terms, quite a few. Oh, this was -4x. Sorry, I made a mistake on that one. Right, it was 6 times -2/3 x, which is -4x. Okay, so we have like terms. I have -3x and -4x is -7x. And then I have +2 and +12 is +14. And now I can subtract 14 from both sides, right? So subtract 14 from both sides, and I get -7x equals -14. And then I can divide both sides by -7, and we get x equals negative divided by negative is +2. And at the end of the test, I would go back and substitute into the original and make sure I get the same value. The third topic says, is something a function based on a graph and a table, right? So, I don't know, if we draw some quick graphs, right? And we say, is this a function? So the key is there any value of x, like here, that gives me more than one y? And there's not, because there's one y that comes out for there. If I pick another value of x, right, like here, there's one value of y that comes out. So this case, it is a function, yes, it's a function. Let's say I had a graph that looked like this, right? I don't know, right? Something like that, right? Clearly, this is not a function, because if I picked this x value, for instance, this one right here, I have one y value there and one y value there. So this is clearly not a function. So that's from a graph. That's relatively easy. Let's take a table, right? So let's say I had an x and y, and I had values, I don't know, 1, 2, 3, 1, 3, 7, 7. Let's do this one first. 3, 7, 7, 3. All right. So when I put a 1 in, a 3 came out. The next time I put a 1 in, a 3 came out. So, and the others, I put a 2 and a 7. I didn't repeat a 2, and I didn't repeat a 3. So these are fine. I'm allowed to have the same value come out with different inputs. I just need to make sure that every time I put a value in, like the 1, that the same thing comes out. So this is a function. Now, if I had x, y like this, 1, 2, 3, 1, and I had 3, 7, 7, 4, then this would not be a function because here I put a 1 in and I got a 3 out. Here I put a 1 in, I got a 4 out. That's not a function, so that would not be a function. For the fourth topic, domain and range of functions from a graph. So I need to look at this graph. So the domain, remember, are all the x values. So if I look, right, this is the x values. In the x direction, this arrow here goes on forever in the x direction this way. And this arrow here goes on forever in the positive x values. So every single number on the x-axis is covered. So the domain is all real numbers. All real numbers, right? And the range for this one is the same thing, right? Because now going up and down, this continues to go up in the y direction, and this continues to go down in the y direction. So every number is hit on the y-axis. So it's all real numbers for the domain, right? Okay. Now let's take a little different graph. Let's say we have this, right? And we have a parabola, right? And let's call this, 1, 2, -2, right? Okay. So the domain, again, is the value for that x can be. So remember, this goes on, and that means it's going to cover every single number going that way. And this goes on, and that means it's going to cover every single number that way on the x-axis. So the domain is all real numbers, all real, right, numbers. You should write out numbers, right? Okay, now the range, though, is slightly different, right? Because the range, it goes up forever, but it doesn't go down forever. Actually, the lowest the y gets is right here at -2. So the range for this is y is greater than or equal to -2 because it can never get lower than -2, but it can go positive forever, right? So y is greater than or equal to -2. Make sure that you use y for the range and x for the domain if you were going to use an inequality for the domain. For the fifth one, it's graphing a complete scatter plot. Now, I'm not going to graph a complete scatter plot for you because we did so many of these, but I am going to give you some of the examples of where people go wrong. So, first things first, if it's just a table of values, x and y, and you do not know what those values represent, it's just x and y, then you would label the x as x and y, and you must use the same scale, This is important. So if your graph paper is like this, and you go 2, 4, 6 here, then you have to go 2, 4, 6 here. Again, if you just have a table of x, y values, that's important. You must do that. Next, when you draw a scatter plot, you don't want the points to be all grouped up here, right? If you had a scatter plot and this was the end result, I would say that's incorrect because all this extra space in the graph is unused. You should change your scales to make it bigger. So the second point is use appropriate scale, so that your graph is not too big or too small, right? Because if it's too small, it's hard to draw a trend line or a line of best fit. Okay, so that's the case where you have an x, y table of values. Now, let's say, however, that we have, I don't know, time and distance, right? Distance. Now, first you'd have to decide what's your independent and what's your dependent, but let's assume time was the independent. So now you would label this as time, and you would put the units like seconds, and this would be labeled distance, and the units, I don't know, maybe feet, right? And then you could use different scale. If this is your graph paper, you could go by ones here, 1, 2, 3, 4, 5. And over here, you could go by 100, 200, because the units are completely different. You can use different scales when you know what the data represents, right? And again, you would want to make the graph appropriate size so that you could graph it, because if your graph looks like this, right, it's easier to draw a line of best fit, and I'm not going to try to draw it without a straight edge, but it would look, right, something like that would be your line of best fit. But if the data is all clumped up, then you would not be able to draw it. So again, if you know what the data represents, you label the axes, but you do not put an X there like that. Don't do that, right? You don't put a Y here, don't do that, because it's not X and Y anymore. It's time and distance. For the number 6, the association of a scatter plot. So first we need to name the association. So this, if I drew my trend line or my line of best fit, right, it clearly would go like this. And that is a positive correlation. Positive correlation. Or the book says positive association, right? Positive correlation. And then we should be able to write an as phrase, right? An as phrase, right? So we would write for this, as the time, right, as x, as the time increases, the distance increases, right? There's the as statement. Because I can look on my graph and I see, as we go this way on time, the distance is going this way, right? So as the time increases, the distance increases. If it were a negative correlation, right, meaning, and this will get confusing, but so let me just, right, I'll draw it in, I don't know, this. If the points were coming downhill, right, like this, right, and the trend line was like this, then that would be a negative correlation, and I would say as time increases, the distance decreases, right? Okay. So you should be able to identify positive and negative correlations. And then, of course, if you had a graph, like this, again, I'm drawing these really quick, right? If you had a graph like this, then you would say there's no correlation. And if it said to write an as statement, you would say there is no correlation between time and distance. If this was time and distance, right? You would just say there's not really a good as statement, right? You would say there is no correlation between time and distance. Okay, for number 7, if we have to draw a trend line. So I drew a trend line through some of this data. Let's assume it was like this, right? Okay, so I drew my trend line. Now I want the equation of that trend line. So what I need to do is I need to find 2 points that are exactly on the grid, meaning on the intersection of the graph. So this point is, it happens to be. If it wasn't, I wouldn't use it. And then I'm going to go up the line, and I see the next point that's like that is this one here. So I'm going to draw my slope triangle, right? And then I'm going to count. 1, 2, 3. Now, this is important before you start counting. If this is going by 1s, right, and this is going by 5s, right, 10, 15, right, maybe we know what the data is, so it's a different scale, right? So now I have to make sure I'm counting based on the scale. So when I go to the right, I go 1, 2, 3, 4. This is a change of 4. But however, up and down, when I go up 1, 2 grids, that's really up 5, 10. This is 10. So the slope, in this case, the slope is the rise over the run. Rise over run. So the slope comes out to be, the rise is 10, and the run, x and y, x direction, is 4, right? So the slope is 5/2. And the y-intercept right here, right, if I do this, right here is at 10. That's the y-intercept, y-intercept. So the equation for this line would be y equals mx plus b, right? And y equals the slope is 5/2, and b is the y-intercept, that's the 10, plus 10. So there's the equation of the trend line. And if it said, predict what would happen when x is 10, so I want to know what happens out here when x is 10. I predict for 10, I would substitute the 10 in. Y equals 5/2 times 10 plus 10. kind of out of room here, but this would be y equals 5 halves times 10 is 25 plus 10 is 35. So the prediction when x is 10 would be y is 35. And if we look, I mean, clearly it's not going to work well on my graph, but let's see if it even came close. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 10, right? And if I go up, right, this is assuming my line was straight over there. I go up to this point over to here, right? That would be 20, 25, 30, 35. Oh, actually it worked out exactly right. That's pretty good. Okay. So again, you can sanity check if it's on the graph. If it's not, like if I said estimate for 100, you clearly can't go out to 100 on your graph. But so anyway, do your slope triangle, get your slope, look at where the y-intercept is, write the equation of the line in y equals mx plus b form, and then substitute it in an x value to predict a y value. Okay, number 8 is very similar to what we just did, but let's just do it again. So let's assume I graphed this line because this was a trend line or a line of best fit, and I wanted to get the equation. So let's do this again. Again, I'm going to pick 2 points, here's one, that go right through my grid. So I got lucky that the y-intercept was right through the grid and this other point. So I'm going to pick those 2 points. I could have also picked this point, right, because that goes right through. This point looks like it goes right through, right? Now, there's a lot of points that go right through. So now, again, let's make some assumptions that our scale is 1, 2, 3, 1, 2, 3. Okay. So in the x direction, it goes 1, 2, 3, 4, 5, 6, 7, 8. This is 8. And then in the y direction, it goes 1, 2, 3. So this is 3. So the slope, right? The slope is rise over run. So the slope is 3/8, right? So there's the slope. Okay. Now the y-intercept we can just look at, right? We're looking right here, and that looks like it's at 4, right? So there's the y-intercept. So in slope-intercept form, it's y equals mx plus b. So we substitute in the slope first, 3/8, and then the b, which is the y-intercept, which is 4. So there's the equation of the line. Right, and then we could use this equation like we did in previous examples to, this is an 8 by the way, right? We could use this to predict y values when x is some number not on the graph, or even some number on the graph, right? We could use it to predict. For number 9, we are going to work with frequency tables. So let's assume that somebody was going to have a party and they wanted to determine whether boys liked a certain thing more than girls, or whether it didn't matter at all. So they were going to see if the activity was dependent on whether you're a boy or a girl, right? So they did a survey, right, and they got some data. So this is the number of boys that voted for those things and the number of girls. Now, I would probably make a guess that the activity is dependent on whether you're a boy or girl, but let's see if that's true. So the first thing you need to do before you start to make your relative frequency table is to determine which is your dependent and which is your independent variable. So in this case, we're seeing if the activity, the bowling, skating, or dancing, depends on whether you're a boy or a girl. So that means the boy or the girl is the independent, and I'm just going to write it so to remind myself, right? And this, the activity, is the dependent, right? Because we're seeing if the activity depends on whether you're a boy or a girl. So if you remember, we now know that we need to total the independent. So in this case, we're totaling the columns, right? Total. If the rows were the independent, then we would total those. So 6, 3, and 1 is 10, 2, 11, and 3 is 16. Okay. So now we can make our relative frequency table. So let's say boys, right? Girls. I'm going to make it a little bigger only because it's harder to write with a stylus. Bowling, and I'm going to abbreviate. You shouldn't, but I'm writing with a stylus, so it's harder. Skate and dance, right? So here's our table, our relative frequency table. So this is our, over here, this is our frequency table. And then what we're creating is a relative frequency table, right? Okay. So now we have to divide by the totals. So this becomes 6 over 10. This is 3 over 10. And this is 1 over 10. And then this is 2 over 16, 11 over 16, and 3 over 16. And we would want to write these now as percentages. So this would be 60%, right? 6 out of 10. This would be 30%. And this would be 10%. And then 2 out of 16, that's 13. I'm going to round, right, to 13. And 11/16 would be 69. And 3/16, again rounded, would be 19%. And by the way, when you round, it is not uncommon for the totals to not add up to 100%, right? In this case, it's 1 over 101 because we're rounding. So now, we created our relative frequency table, and now we need to see if, in fact, the activity is dependent on the boys or girls, on whether you're a boy or a girl. So now we're going to compare the dependent variables, right? So now we're going to look at this 60 and this 13. If they're the same percent or very close to the same percent, then there would not be an association or a dependency. In our case, the 60 and the 13 is very different. The 30 and the 69 is very different. And the 10 and the 19 is different. So in this case, we would say there is a correlation on the activity based on we could say gender, right? Which means that the activities do depend on whether or not you're a boy or a girl, your interests, right? So I would say that this is probably what we would assume to happen. But we've actually proven it because the percentages, the relative frequencies are drastically different. Look, 60% of the boys said they would like to go bowling, but only 13% of the girls said it. Clearly, there's a difference based on gender. Even skating, 30% of the boys said they wanted to go skating, and 69% of the girls said they wanted to go skating. So again, clearly a difference. Even the last one, dance, 10% of the boys said they wanted to dance, and 19% of the girls said they were dance. That's a far enough difference to say that the activity, bowling, skating, or dancing, does depend on whether or not you're a boy or a girl. Number 10, ratios and proportions. So let's take an example. Let's say that we have a model of a building. I don't know, so here's a building, right? Let's say here's our building, right? Windows, right over. Okay. And in our model is 12 inches wide, right? And 8 inches high. Okay, here's our model, right? Model building. Now let's say the real building, and again, these are hypothetical numbers, right? The real building is 240 inches wide, right? Again, pretty small building, but okay. And I say, how high is the building, right? So what's this? What's the height, right? So to do this, we would set up a proportion, right? That the 12 inches of the model, right? 12 inches of the model is 240 inches in the real building. And that has to be equal to the 8-inch height in the model over the height of the real building. So we'll call that, I don't know, H, right? H. So there's a lot of ways to do this. I would probably say that the first thing to do would be to reduce this first one to 1 inch over 20 inches, right? Because they had a common factor of 12, right? So that's going to make it much easier, right? 8 inches to the height. Now, there's lots of ways we can do this. We could cross multiply, or we could see what happened in the numerator. So clearly the numerator got multiplied by 8. So the denominator has to get multiplied by 8, and we would get the height, equals 20 times 8, 160 inches, right? Or we could have, taken another approach. We could have, right here, done cross multiplication. We could have said, 20 times 8 equals 1 times h, 160 equals h, right? Either way, we could have h equals 160 inch, right? Either way, you could cross multiply like that, or you could have used what was happening in the numerators and denominators. Again, the key is, however, to show this, to set up the proportion and show that work. So in this video, we've covered all of the topics on the test. Clearly, you should be studying more difficult problems than the ones I gave as examples, but this should be a good foundation for the upcoming test. I highly recommend you go through the homework problems on the review sheet and watch videos for any of those homework problems that you were unable to do. In any case, good luck.